Welcome back to Practical PyTorch. In this video, we look past a single accuracy number. Our model gets about 3 in 4 images right. That sounds fine, but one class fails badly, and a single number never tells you which. So we build a confusion matrix. It shows every right and wrong call class by class. By the end, you will read precision and recall straight off it. Last time, our augmented model got about 3 in 4 images right. That one number sounds fine, but it hides a lot. One class is right less than half the time, and the number never says which. A confusion matrix opens that number up. It shows every right and wrong call, class by class. This video has 3 parts. First, we read the confusion matrix. The diagonal is right, off the diagonal is wrong. Second, we build precision and recall from the same table. Each one is just a row or a column. Third, we show how one accuracy number can lie. That happens on imbalanced data. First, the confusion matrix itself. Every right call sits on the diagonal, and every mistake sits off it. Take 5 classes: cat, dog, bird, deer, frog. Each row down the side is the true class. Each column across the top is the class we predicted. A row and a column meet in one cell. This grid is empty for now, just a place to point. Now fill in the counts. The diagonal runs from top left to bottom right. This top cell is the cats we called cat a hit. Same story here. Birds we labeled bird. The true class equals the guess. And frogs we labeled frog. These counts are round numbers just for the picture. Every cell on the diagonal is a hit. A perfect model would fill the diagonal and leave the rest empty. Every off-diagonal cell is a mistake. Take this cell. True deer predicted bird, a wrong call. The ringed cell is the worst pair. Follow the cat row across to the dog column. Those are true cats the model called dogs. Still round numbers just for the picture. That was 5 classes with round numbers. This is the real matrix, all 10 classes. The bright diagonal holds the correct images. That is 7,498 out of 10,000. In percent, 74.98 overall. The cat row is the darkest, so cat is the weak class. Its brightest wrong cell sits in the dog column. 201 cats were called dogs. This run was measured on a Tesla T4. Second, precision and recall. Both come straight off this table. One is a row, the other is a column. Recall reads one whole row. Walk the cat row across. Here cats were called dog, a miss. Here cats were called bird, another miss. Here cats were called deer. And here cats were called frog. Every one of these is a cat we missed. This diagonal cell is the cats we got right. Recall divides it by the whole row total. On the real 10 class model, cat recall is 46.9%. Fewer than half the cats were found, measured on a Tesla T4. A row is recall. It asks, of all the true cats, how many do we find? Precision reads one whole column. Walk down the cat column. Here a dog was called cat, a wrong cat call. Here a bird was called cat. Here a deer was called cat. And here a frog was called cat. Each one is a false alarm. This diagonal cell is the true cats. Precision divides it by the whole column total. On the real model, cat precision is 66.06%. When it said cat, it was right about 2 times in 3. That is measured on a Tesla T4. A column is precision. It asks, when we said cat, how often were we right? Third, where one accuracy number lies. Watch what happens on imbalanced data. Picture a dataset that is 90% negative. Only 10% is positive. A lazy model answers negative every single time. It never once says positive, yet it still scores 90% accuracy. Accuracy hides the failure completely. The model never predicts positive, so the positive column is empty. Remember, rows are the true class, columns the predicted class. An unpredicted class leaves an empty column, impossible to miss. Let's review. The diagonal is what the model got right, the correct calls. Every off-diagonal cell is a wrong call, and it shows you exactly where the model went wrong. Read a row and you get recall. Read a column and you get precision. So one accuracy number can hide a failing class. Next time, we look at transfer learning. Your turn. A dataset is 95% negative. The model always answers negative. What is its accuracy? And what is its recall on the positive class? Pause and work it out. Okay, here it is. Accuracy is 95%, but recall on the positive class is 0%. It never once predicts positive, so the whole positive column is empty. That one look makes the failure obvious. We trained this small model from scratch. Next time, we borrow a network that already learned what edges look like. We reuse what it knows instead of starting over. See you there.